Thank you for attending today's webinar on simulating SAR using reality capture and Ansys simulation software hosted by Rendered.ai. I'm excited to get a chance to share expertise from both the Rendered.ai and Ansys teams and how you can improve your SAR simulation, especially for large environments. If you have any questions throughout the presentation, feel free to add them to the Q&A section below, and we will respond at the end of the session today. So, quick introduction. My name is Jeffrey Ian Wilson. I'm the Technical Director of 3D and the Customer Success Team Manager here at Rendered.ai. I have an extensive background in games and visual effects for both television and film, and an extensive background in reality capture techniques, including aerial survey, LiDAR, and other terrestrial sensor systems. Michael joins us is also an engineer here at Rendered.ai. Works closely with our customers to develop simulation assets for a wide range of applications within the Rendered.ai platform. He's especially knowledgeable in electronic warfare and radar systems, which is very useful for our defense and intelligence customers. I'm excited to have Ariane from Ansys joining us today. Ariane has a long-standing role at Ansys as our senior product specialist for RF and microwave and R&D. He is responsible for the SBR product portfolio at Ansys, which includes the Perceive EM simulation software that we will show today. Thank you, Ariane, for being here. This slide, I wanted to give a personal experience on my experience with the AI systems. In my previous work at Eyeline and Netflix, I had a computer vision problem, and I encountered these very items that I'm about to discuss. Data is the limiting factor for AI. There's cost and time. Real data is expensive and unavailable or impossible to acquire and label. Bias, it covers rare objects and stereos, which are hard to capture. Innovation, without data, it's impossible to explore new sensors and data types. And accuracy, data labeling is imprecise and incomplete. And my personal experience, and how I ended up here at Rendered.ai is I had a computer vision problem with a very large aerial survey and capture of Rio de Janeiro. And I had to segment and scrub vehicles from the roads, and the aerial data packages and models that I had access to were trained on areas that were outside the area of interest. So what happened is I needed to generate synthetic data because we can't send a helicopter up in every location to try to scrub this data from it. I also had issues with annotation. Annotation was subject to error. I personally had experience with using a number of annotation platforms online. And one of the great things about synthetic data is it's 100% accurate, as far as the annotation. Every annotation is perfect. It's just a question of generating a large database of imagery to work with. Next slide. So Rendered.ai provides the compute and content to make synthetic data a reality. We build different channels based on different simulator types. As I mentioned, it's 100% accurately labeled. We support synthetic aperture radar, X-ray, and RGB spectrum, as well as simulators such as DERSIC, which is a spectral physics-based simulation system. Our platform allows you to customize your content, manage your content, we can help you or help integrate your own data sets to create a scenario, manage a library. We can post-process the data, even apply a CycleGAN, which is an interesting technology which can take the synthetic data and actually, apply a style transfer that increases the realism of the output while maintaining the annotation. In addition, we can do machine learning integrations, assess the data quality, help you work with our Rendered.ai platform, and as well as other compatibilities. One of the unique benefits of working with us is, you mentioned that synthetic data is approximately 25% of the cost of real data. We can generate a diverse data generation set for training and validation, 100% accurate labeled, and then a cloud-based platform, data set comparison, and it's similar agnostic. Our platform can actually be used to generate a scene and actually use whatever simulator that might be. So, and there's have a robust subscription options. So at this time, I'm happy to turn it over to Arian to discuss the Ansys Perceive EM simulator.
Thanks, Jeff. It's kind of an exciting opportunity here to introduce the Ansys capabilities, but doing so in a kind of a different method than we've typically traditionally do at Ansys, and offering our physics-based simulation capability embedded inside of another platform, and that platform is Rendered.ai. In this case here, for those of you who aren't familiar with Ansys, Ansys offers physics-based simulations across all domains. Here we do fluids, structurals, electromagnetics, optical, even digital mission engineering. So we have all these physics-based capabilities. As these engines kind of evolve, we want to look at how can we deploy these in different workflows. And one of those workflows is through this Rendered.ai platform. So on the next slide, what we'll talk about is how we're taking this electromagnetic simulation capability that we offer as it's a physics-based simulation, and we're offering and introducing this new solver called Ansys Perceive EM. Ansys Perceive EM is an electromagnetic solver. And in particular, today, what we're going to look at is how we can take this solver and employ it to do synthetic data generation for a radar imaging application. So on the next slide, what we're looking at here, what is Perceive EM? So for those that aren't aware, Perceive EM is a brand new tool that we've introduced that is a GPU accelerated shooting and bouncing radar, SBR solver. What is really unique about this, aside from it being very fast, it's a solver that can solve things in real time, faster than real time, or kind of near real time, is that it's delivered as a lightweight API. And as a lightweight API, that means that it can easily be integrated into other workflows like the Rendered.ai workflow. And that API, you interact with that by introducing things like geometry, kinematics, the waveform, antenna patterns, and it outputs raw IQ data. So what we've done is we've taken this API, and if we go to the next slide, we'll look at basically how this API can then be deployed in that Rendered.ai platform. So what that means is Rendered.ai is handling the scenario management, the post-processing, the taking the results from that simulation and putting it in a way that you can use it for AI, ML, or just in general data management. The platform itself is handling the input parameters. So as on the previous slide, I mentioned, those input parameters are like the geometry, the kinematics of the scene. That's what the platform is doing, is it's managing those input parameters, putting it into this physics-based simulation engine, Perceive EM, and then returning data into the rendered platform for further processing. So on the next slide, what we'll look at is a little bit more detail on this solver. So what makes the solver unique beyond that it's an API and it's very fast? Well, one is we can introduce realistic environments, realistic scenes with antennas and dynamic motion into the scene. So you can see a couple examples here of different types of problems we can solve. Looking at communications problems or autonomous vehicles, and what we're going to focus on today is the radar imaging. And we're doing this with this high fidelity shooting and bouncing ray solver that's based on HFSS SBR Plus technology. So if those of you familiar with HFSS, within that there's HFSS SBR Plus. This solver engine is based on that technology. And under the hood, what it's doing that's unique is that it's based on a hybridization of physical optics and geometrical optics, which lends itself very well to these radar imaging applications or radar sensing in general, where we can generate high fidelity radar returns of complex environments. And so how do we do that? So on the next slide, I'll just show you a really kind of brief idea of how this works. And when we talk about SBR, what we're doing is starting with the geometry, which is made up of triangles. So that's kind of what you see here, a simplified version of that. These triangles are then illuminated with rays. So we illuminate the scene with rays using this kind of the physical optics approach, where these rays are used to estimate currents on all these triangles in the scene. So the rays themselves are just ways of depositing currents. And those currents then are extended to multiple bounces through geometrical optics. So now we're adding up currents on triangles. The important part here now is that we have all these currents in our scene, that the rays no longer become important. Now, once we've illuminated the scene with rays and extended it to multiple bounces, we have currents that are all over the scene. And the major point here is that we're radiating all those currents to a receiver through this kind of wave propagation method, not through that abstraction of rays carrying the energy. So we're using real radiated equivalent current sources to see what that radiation is to our receiver. So on the next slide, we're looking at, what does this partnership mean? What does a partnership between Rendered.ai mean? Well, one is it enables us to embed physics, not just electromagnetics. We could extend this to multiple different types of physics, but specifically today, we're looking at this Perceive EM electromagnetic solver based on that shooting and bouncing ray to do SAR analysis. And we're looking at large scenes, so multiple kilometers by multiple kilometers in size. The speed at which we can generate these images is very quick. And the idea is that now Rendered.ai's platform can then be used to configure the scenes, change assets around, and then organize and manage all that data. So this partnership is introducing these two different companies, Rendered.ai and Ansys, collaborating into a way to provide a product that gives us kind of the best of both worlds. Rendered handles the data management, Ansys handles the physics-based simulation. And with that introduction to Ansys Perceive EM, I'll pass it back to Jeff, I think, to continue on. Thank you.
All right, thanks, Arya. So now I'm happy to show you a real-world example where we took the Ansys Perceive EM simulator and combined it with a reality capture. Slide. So, give you a frame of reference. I'm teaching an online masterclass on 3D scanning. It was unrelated to the work and more of a side endeavor, a personal passion of mine, where I was capturing an area where I have permits to scan from the air and ground an abandoned Air Force base near Victorville, California. Part of that lesson plan was to cover aerial photogrammetry and survey with ground control. You may ask, well, what is aerial photogrammetry? And aerial photogrammetry is the taking multiple images and how they overlap to actually build a 3D scene. One aspect of this is ground control and GNSS stations. So I have maintain a very high accuracy, spatial accuracy. You know, through the processing, I was able to get about a centimeter accurate, spatially accurate image, scan with a 3 centimeter ground sampling distance resolution. As a part of this process and the way I work in reality capture, I always export in a number of different formats because I'm not sure how I'm going to use it in the next step and wanted to provide the most amount of flexibility, which leads me to the next item. So I had already generated the scan, processed the output for variable use cases that I hadn't determined yet. And then when it came, this project came in to use the Ansys simulator, and we had a requirement to build a scene for it. It occurred to me that I already had a capture at a high resolution that fit the requirement of 3 to 5 centimeters per pixel resolution. And so I spoke with Michael, our engineer and resident SAR expert. Can I use this data with the simulator? And he said, of course. So what it allowed us to do was take data that was generated for another use case or indeterminate and actually use it and apply it and test it inside the Rendered.ai platform. And then it added not only value to the scan that I had created, gave me another use case, but it also explored and tested out using reality capture in the rendered AI platform. So this is going to be an actual demonstration with Mike on how the scene is generated and implemented. Thank you.
Forgot to share my video. All right. Yes. So just to give a quick primer on for people who are unfamiliar with the Rendered AI platform, we present a no-code way to generate synthetic data. And the way we do that is this node graph infrastructure. This example is one way that we use to set up a SAR simulator. And this is how we incorporate models into the scene. So this channel has pre-existing models like aircraft and ships and tanks and other ground vehicles. And you can click those aircraft and bring them into the scene and incorporate them like that. If you have a model of your own, you can load it onto our platform, onto a workspace volume, and it'll show up right here. So for this example, I created a 200-meter square kind of concrete slab that I can place objects on top of. You click that and you drag it on, and you can place it on the screen. You can place it in the scene. Set object position, and so I can drag this object or link that object there and place this object in the scene. And so now I have two objects in the scene that I can control their position and attitude relative to each other. And you can imagine I can build this out to as complex a scene as I want. The graph just gets larger and larger. You just have to zoom out further and further. But once you're done there, you click stage and you kick it off. Now, I'd like to show you how we would incorporate the Perceive EM API into this kind of node graph infrastructure. Megan? So this is an example of how we would wrap the Perceive EM API in the rendered platform. The decommissioned airbase would be loaded as a workspace object. It would go into a workspace volume. You could load it here and set its position. And here we have we can control its rotation, and we're doing a roll, pitch, and yaw. So yaw is, the heading. And so we're sweeping the heading from 0 to 360 degrees every 5-degree step. And that's the entire scene. Now you can put your entire scene into one model, or you can break your scene up into separate models so you can move them with respect to each other. But we're doing it all in one just for simplicity here. That scene goes into the generate images node as well as the Perceive EM simulator. If we go to the next slide, what you're seeing is essentially the code behind what these nodes are doing. The decommissioned airbase is just loading this STL file that comes pre-existing with the channel, or that the user can load up on their own. Setting the scene coordinate system is really just that. You can select the position, the velocity, the rotation, several different kinematic operations. So if we go to the next slide. The radar, as you might imagine, is a little bit more complicated. Here, in this case, we're setting up the antenna parameters for the antenna patterns for the transmit and receive patterns. They're both going to be vertically polarized, and they're both going to have 1.8 degree beam width in vertical in both phi and theta. For those that understand what that means. We can also select the waveform. And so here we have a chirp, with an ascending ramp. centered at 9.65 gigahertz with a bandwidth of 1 gigahertz, which should give us a roughly 1 foot range resolution. And these are all the parameters that we use to set up the waveform. We can also set the position of the satellite. And so as we know, the satellites are about 500 kilometers-ish. I think that's for LEO in space, with a speed of around 5 kilometers per second. Now right here we have set up a linear motion, but if you wanted to use the exact parameters from a Capella satellite dwell, like the exact positions and rotations, you could load that up into the simulation. Next slide, please. And lastly, we have the ability to generate images. So we can select the number of pixels that we have that we want for the final image. Right now, I'm using 1024 by 1024. I've always been a fan of Power 2s, and so that's what I use. But we have a Haining filter for range and Doppler, and this is how it all gets applied. And once that's all done, you can go to the next slide and run the simulation. So as you can see, this is what we come with. This on the left side. This is what the input data is. It's the result of Jeff's photogrammetry adventure, and it generates an amazingly detailed mesh. I'm not experienced with photogrammetry, but it seems it's quite good. And and in this example, we actually have the ability to place, since these are meshes, we can place our own meshes in this scene. And so if you look carefully, I don't know if you can see my mouse or where I'm pointing, but you'll see 3 tanks that are placed in this scene. Those are not really there, but we have separate CAD models for all kinds of military platforms and civilian platforms, and we could put in an Airbus A380 on the road here if we wanted to. It wouldn't be realistic, but you could do that. And then if we go to the next slide. And this is the resulting imagery. I like to go shadows down. Some people like to go shadows up. It's okay. It's all a personal preference. It's all about what you're acclimated to. But this is what we can generate when we use the physics-based Perceive EM simulator and combine it with the photogrammetry result of people going out and doing really interesting photogrammetry research and building these meshes. The next step here is to probably apply materials to each component in this mesh. Right now, I believe we're just using metal or PEC. But moving forward, I'd like to apply real materials to the trees, to roofs, roads, and the dirt. And as we increase the realism that we add to this physics-based scene generator, because it is physics-based, the resulting image will inherently become more and more realistic. And that's what I find quite exciting about physics-based simulation. Next slide, please. Yeah. So does anybody have any questions? I've been trying to answer them in chat as fast as I can. I can take on a couple of these. So do you need 3D models for the entire scene? So you need 3D models for whatever part of the scene that you'd like to simulate. As you saw in the example, I had a 200-meter concrete slab. If you want to simulate anything outside of those 200 meters, then you need a model to cover that. You would need a 5 kilometer concrete slab. In this case, we're using the result of photogrammetry, which I believe is 2 or 3 kilometers on a side, which is quite large. But again, if you want to simulate something larger than that, you would need a model, a 3D model that is of the size. Curious about integrating these solutions into ArcGIS Pro. Are there any thoughts about this software engineering platform and infrastructure design? I am not an ArcGIS person. or a GIS person. So I'm not sure I can answer this, but I definitely know some people, and so we can definitely refer this to them.
I would say that, given the nature of the platform itself, it's a bit like data agnostic. It's just a question of if the data is formatted in a way that's friendly to whatever simulator we're providing. We've done some work on an ArcGIS channel, so I know that we can accomplish that. It's just a question of what kind of data inputs are you looking for. We can actually take in chips and imagery, satellite imagery. It necessarily doesn't have to be a complete 3D scene, but I know that we can support maps and ArcGIS tiles and the tile format. It's just a question of actually properly setting up the simulator.
The next one is if the entire scene is the 3D model you are rendering, how are you ensuring the material properties of different objects in the scene? So I can actually defer this to Arian. I think he's got the best answer for this.
Yeah, so there's a couple of different ways that we can handle material properties, and in the model, the API itself, it supports material properties on a per triangle basis, meaning that every single triangle in the scene can have any material properties. That includes transmissive materials or reflective only materials. So you can have materials that allow rays to penetrate through and continue on, or rays that only bounce off of the surface. So the material property definition is very general. So any electromagnetic properties can be applied to the triangles. For the scene itself, aside from being able to apply those material properties to each triangle, you could also segment the model through either a definition of where the source geometry comes from. It could be as simple as buildings, terrain, and cars, something like that, as they're segmented and separated. Or you could be more detailed and actually come from a texture map that includes textures directly relating to material properties. So I guess the short answer is there are various ways that we can handle material properties, and it just depends on the type of results that you're looking for and which is going to be the best approach to that.
Great.
I can take the next question.
You want to keep going?
Yeah, there's are we producing amplitude intensity only, or is this model also create phase information? So the output from the simulation is actually raw IQ data. So we have real complex values coming out of the simulator, which could then be post-processed into images using various imaging processing algorithms. What we're seeing here is the image processing that was used as a simple Fourier processing, where we're looking at that raw IQ data with Fourier transforms across the frequency and chirp dimension to formulate the image. I could take the next one as well. On the Ansys side, what other EM solvers besides SBR can we use to accurately model the antenna within this workflow and platform? So for those that aren't familiar with Ansys, we have a tool called HFSS. HFSS is kind of known as the gold standard for antenna modeling or component level modeling of any type of geometry. So the source for these antennas that are coming into the simulation could be measurement, could be ideal kind of parametric defined antenna patterns, or they could be realistically simulated using HFSS as we put in the real geometry into HFSS and actually simulate a virtual or digital twin of that antenna model. Maybe, Mike, I'll let you take the next question.
Sure. So yes, it's highly dependent. So the question is, real X-band SAR is typically fairly noisy, perhaps noisier than the example that you showed. Do you have post-processing routines that can generate realistic noise as well? So, I'm sorry?
So Mike, sorry, I could take that if this is related just specifically to the API. The API itself does allow you to add thermal and phase noise directly to the simulation at the level of the physics. So we're actually adding, for example, phase noise is embedded into the electromagnetic solution. Noise beyond the thermal and phase noise would need to be added in post-processing, and it's not currently done within the API.
But no, I don't know if we have any further routines that add noise. I mean, a perfect example of that would be speckle, which we don't support right now, but we could. Can this simulate SAR images of maritime vessels in different sea states? I'm sure it could. The problem with that, and maybe Arian, if you have a better answer, is modeling the sea states.
Yeah, so sea state is a complex problem. So our simulator can handle dynamic scenes where things are moving. What's happening though in a lot of the dynamic scenes that we're modeling, we're using rigid body dynamics. So things that are moving and we're assuming are rigid and not morphing in shape like a sea state. So although we can input a sea state into the simulator, we're kind of going to have to make the assumption that we have to follow kind of that rigid body dynamic assumption that current sea state is going to persist across all the chirps in the image generation. We could add velocities and orientation and movements to that sea state, but that's something that we would need to explore in a little bit more detail, as it is a fairly complex type of problem.
I could add some clarification. On the platform, we use and internally we use on the platform simulator we use Blender. Blender does have some fluid dynamics capability to render out the waves and geometry in there, as well as more accurate fluid and gas simulations inside another tool called Houdini. So we can provide that as a sequence of OBJs that may be able to help process that, as well as the segmented materials from foam to the wave, the depth and some of the properties of the water.
Yeah, for those of you that are working with geometries that contain sea state, that would be something that I would suggest reach out to Rendered or to Ansys. We'd love to work with you a little bit more closely on that, because there's not a one solution for everybody's problem. But we do have some ideas, and we have been working with some customers that are modeling different sea state types of geometry. I could take the next question. What if your scene contains many trees, but not so many to create a dense forest, but enough to hide things of interest? Would the increase in what would the increase in computational cost be? So the solver itself handles any materials, including trees, and those trees can have rays that penetrate through those. Each time a ray penetrates through a surface, it generates a reflected ray and a transmitted ray. So there is an increase in computational cost. It's hard to say exactly what that would be, but the solver itself is very efficient in that it can handle millions and millions of rays, and it can batch those rays out as it needs to kind of deal with the increased computation. So we can handle this. It's going to be scene dependent. But yes, you are correct. There is going to be some cost computationally as you add more transparent or semi-transparent geometries into the scene.
Mike, we had a question about use cases for agriculture, like crop type mapping, yield prediction, etc.
Yeah, the complex aspect for agriculture and essentially all non-man-made things, and even man-made things, is getting accurate material properties for those objects in the scene. I imagine you're trying to see if they've gotten enough, if the crops have gotten enough water, which would change their reflectivity, their electromagnetic properties in the scene. I'm not sure of any research, and maybe I'm sure there is research that covers that, but the hardest part of that project would be gathering the electromagnetic properties for different types of crops and different types of crop states, whether they've got a lot of water or a little water, or if they, any of those states that they may have. So that's the hard part there, is getting electromagnetic properties. Once you have the properties, You can apply those to the mesh, just like Arian said, and run the simulation. But as I said, the hard part is those material properties. Arian? Yeah.
So the next question is, does this workflow support multi-static SAR simulations? Yes, the workflow we demonstrated today it was basically a monostatic case where transmit and receive were co-located on the same platform, but there's no limitation. Transmit receives can be arbitrarily defined in any location, as well as any number of transmitters and receivers. So bistatic SAR simulations with multiple element arrays are all possible with this workflow. The next question is, how long does it take to simulate a single SAR scene? So it depends on the complexity. If you're talking about a vehicle, if you wanted to image a tank or a ship, it could be on the order of tens of milliseconds to generate an image. For larger scenes, like the scene you were seeing here, I believe that was on the order of a minute to capture that entire scene. But it also somewhat depends on the GPU hardware that you're using. As I mentioned before, this is a GPU accelerated solver. Whether you're using an RTX 6000 or an older generation GPU, is going to have an impact on how long the scene takes to simulate. But on the order of, for simple images, of tens of milliseconds to a minute for the larger scenes.
We have another question on, are there other radar physics we plan to support besides SAR, such as radar tracking? Mike?
I mean, that is definitely something that I'm very interested in. Arian, I'm not sure if this is something that Ansys is open to doing.
Yeah, so the API is general enough that it would support it. And it's really what Rendered is offering is the platform to enable any type of simulation that could be supported by a physics-based solver. So I think that at the API level, Perceive EM would support that type of simulation. And it's more of a, how do you want to build the workflow? And I think that's kind of would come up with the specific type of use case.
So this next question is, does Perceive EM support high forward squint angles? And I believe since Perceive EM is a physics-based simulator that supports an arbitrary geometry, user-defined geometry, I believe this is true. I believe it does support high forward squint angles. And so I think the answer is yes.
Okay. I want to answer, we had a few earlier questions that were answered. I want to go through them for the recording. Do we plan to post a link to the webinar? Yes, there'll be a recording that'll be available shortly after on YouTube. Another question, how does Ansys tool and the rendered AI system actually connect it? Do we have to have an account set up with both? Mike?
Oh, my response was that it's not required to have accounts on both. A subscription with Rendered AI will include a subscription to Perceive EM. Arian, would you like to add on?
Yeah, that's the basis of this partnership is Rendered AI offers a workflow, and that workflow would kind of support this physics-based simulation embedded within that workflow. And along with that goes the subscription-based model that they're using, that the solver itself would be available within that subscription.
Right. We had another question about consideration challenges when you're integrating FEM, BMS. Mike, could you answer that?
Right. So I believe that it has to do with the 5G broadcasts and that kind of infrastructure. I'm not very familiar with 5G, but I'm quite confident it doesn't interfere with X-band. Specifically, where we're operating is at 9.65. That's where Capella and ISI and a few of the other commercial SAR providers operate. So I don't believe they conflict, and so that should be a non-issue. The next question that I had answered in chat is that if someone asked if they could use their own 3D assets in the scene, and yes, during my little short demonstration, I think I mentioned that users can load up their own models into a workspace volume, and then that will turn them essentially into a node that can be dragged out onto our node graph architecture, so they can be used in the simulation. So if you have your own 3D assets that you've created from photogrammetry or Blender or any AI generated 3D assets, you're more than welcome to load them up on the platform and see how they look in SAR.
There was an earlier question that I wanted to elaborate on about assigning materials. That's consistent with my experience working with aerial imagery and LiDAR, that a lot of the classification tools for classifying point clouds and reality capture data, it's object-based, not material-based. But a novel use of our platform would actually to be able to train a computer vision model to break an object down by materials instead. So the scene of the capture I did that's just a small section. It's up to almost 2 kilometers is the entire area. And there's more than enough data for me to either manually annotate or use the Rendered.ai platform to generate a synthetic scene and break it down my materials. So I'm creating a computer vision model that will actually segment the scene into materials and actually use those material ID maps to map to SAR compatible materials. So there's a way to use the render platform in another way to solve another problem, to use another simulator and automate that procedure. There's another question. We dropped the link for the YouTube channel. Asked Megan. Hopefully she'll get back to me on this one. We have another question. Can Rendered.ai generate synthetic data that includes both spatial and spectral images, specifically for working on tasks like land cover, classification, disaster, flood event, extent mapping, which requires high resolution spatial data as well as spectral information? Hey, Mike, it's a good one for you.
So let's see, include spatial and spectral images. So I believe this is asking if we support generating synthetic data that is not in addition to SAR. In terms of EO and IR, electro-optic and infrared, we do. Tasks like land cover, classification, disaster, flood. The lift would be creating these scenes, and so with the associated meshes required to and material properties required to represent them properly in each of the appropriate simulations. Yeah, I think I answered the question.
Yeah. To answer the question about the link for the YouTube channel, if you're registered for this webinar, you'll get a follow-up email tomorrow, which will have links to the YouTube video.
Jeff, I think this next one's for you.
Okay. And a typical workflow involving drones and cameras for data capture and analysis. What is recommended physical order of operations, and how does the sequence impact quality and efficiency of the data collected? Let's see. I think it entirely it depends upon the desired ground sampling distance, and for what you're trying to simulate and train. In my case, 3 to 5 centimeters was my target for my aerial imagery, because at that resolution, it connects with ground captured information like terrestrial LiDAR, DSLR photography, and other sensors that I was using. The lower you get to the ground and the higher the resolution, the longer a capture takes. So, the physical order of operations is dependent upon the size of your capture that you need to cover, the ground sampling distance, which is related to how high or low the drone or aircraft flies, and then the amount of time that you need to capture in. In the case and for the Georgia Air Force Base, I had a limited window of time because for visual effects and games applications, I'm trying to maintain the lighting consistency of lighting. So I had to adjust the altitude based on that. So the fly higher and cover more ground, but I lose resolution. So it just really depends upon what your needs are, and then the resolution required and the sensors that you're employing. But all of that can impact the quality and efficiency. It's just a question of planning those things out. All right. Do we have any other questions? I think we've covered most of these. Okay, looks like we've done that. I had one pop in here. Is it possible for a customer site to host a local instance of Rendered.ai and Perceive EM due to security concerns? Mike?
So we have very recently updated our platform to support on-site deployments. We have not talked with Arian or Ansys about the idea of doing on-site deployment of Perceive EM, but I guarantee it is a possibility.
Yeah, I think it may require just some discussion with both Rendered and Ansys, but I do believe we can make that happen.
All right, it seems like we've answered all the questions. Anything else before we go? All right. Well, thank you for joining us. We appreciate your time. Feel free to follow us up on our website or contact sales, and feel free to reach out to myself on or Megan or Mike or Arian on LinkedIn. Thank you very much.
Thank you.
Thank you.